Look around the room and pick one thing that is at rest. Not slow, not quiet, at rest. You just chose something that is moving, and you had no way to know it. Not because you were careless, because your eyes were never built to resolve it. Now try the harder version. Sit still. You were told to do that your whole childhood. In classrooms, at dinner tables, in waiting rooms. Sit still. You never once managed it. Not for a second. Not because you fidgeted, because it cannot be done. Here is how we know. Lie down inside an MRI scanner and the technician will ask you to stay perfectly motionless. At the scale of your body, you can. You will hold that position without a visible tremor. And while you hold it, the machine measures the water molecules moving through your tissue, not your breathing, not your pulse. The molecules themselves, wandering through the cells of a body that is, by every visible standard, completely still. There is an entire branch of medical imaging built on that motion. Doctors read it to map the structure inside you. So the stillness was real, and it was also incomplete. That gap between what looks still and what is measurably in motion has a history, a number, and a proof. And a great deal has been sold on top of it that the proof does not support. By the end of this video, still will stop being something you observe. It will become a question you ask. Stillness is not an illusion. It is a level of description. And once you can see the levels, you cannot unsee them. In 1905, Albert Einstein asked what should happen to tiny particles suspended in a liquid that looked completely motionless. His answer was quantitative. If molecules were real and thermally agitated, the visible particles should wander in a precise statistical way. A few years later, Jean Perrin measured that wandering and found the prediction held. That result changed more than the status of atoms. It exposed a trap built into ordinary perception. Stillness can be real at one scale and false at another. A glass can sit motionless on a table. The liquid inside can look calm. Yet microscopic particles suspended in it can execute an irregular dance because molecules too small to see are colliding with them from every direction. The world you experience as solid, quiet, and stationary is often only solid, quiet, and stationary at the scale your senses happen to resolve. That discovery is extraordinary. It is also the most borrowed result in modern mysticism. And the borrowing changes what it says. The important point is not that Einstein discovered everything vibrates. He did not. Brownian motion is not a universal vibration law. It is random motion produced by microscopic thermal agitation. The distinction matters because several popular claims blur very different kinds of motion into one word. The first claim says Einstein proved a spiritual law of vibration in 1905. He did not. His 1905 paper was about molecular-kinetic theory and the motion of suspended particles. The famous metaphysical phrase, "Nothing rests, everything moves, everything vibrates," appears in the Kybalion, published in 1908, 3 years later. A second claim says that because matter contains motion, every emotion, thought, or life circumstance must also have a physical frequency that can attract matching events. That leap is much larger than it sounds. In physics, frequency means something operational. An identifiable variable oscillates, its cycles can be counted, and the result can be measured in inverse seconds. If someone says gratitude has a frequency, the scientific question is immediate. What exactly is oscillating? What instrument measures it? And what causal mechanism connects that oscillation to an external event? Without those answers, the word frequency has changed jobs. It has moved from measurement into metaphor. So what, exactly, is hiding underneath ordinary stillness? Einstein did not merely say that unseen molecules might be moving. He built a bridge from invisible activity to a visible measurement. Imagine a tiny particle floating in water. It is struck by water molecules from all directions. Over a very short time, the impacts almost balance. Almost. The particle receives a little more momentum from one side than another. Then the imbalance changes. The result is not a smooth oscillation. It is an erratic walk. Einstein showed that this apparent randomness should obey a statistical law. For ordinary one-dimensional diffusion, the mean square displacement grows in proportion to time. In simple form, the relationship is mean x squared equals 2 dt, where d is the diffusion coefficient. That sentence looks modest. Historically, it was devastating. If the molecular theory of heat was right, then a quantity no one could see directly, the agitation of molecules, would force a visible particle to wander by a measurable amount. Temperature, viscosity, and particle size entered the calculation. The invisible mechanism now had numerical consequences, but Einstein was careful about what he had done. The 1905 paper was a theoretical derivation, not the final experimental verdict. He explicitly treated observation as the next step. If the predicted motion was found, measurements could be used to estimate molecular quantities. If it was not found, the molecular-kinetic explanation would be in trouble. That second step came through Jean Perrin, beginning in 1908 and culminating in his major 1909 work on Brownian motion. Perrin studied suspended particles and compared their behavior with the statistical predictions. He used multiple methods to estimate molecular constants and found converging values. The results became powerful evidence for the atomic and molecular picture of matter. So the historical sequence is clean. Einstein, 1905. Derivation. Perrin, 1908 to 1909. Experimental confirmation. That is stronger than a vague claim that science discovered everything moves. It tells us exactly what was predicted, exactly what was measured, and exactly where the evidence came from. And it reveals the first form of hidden dynamism. A liquid that is stationary as a whole can still contain ceaseless microscopic motion. The obvious next question is harder. Does the same principle survive when matter looks not just calm, but rigid? A metal bar on a desk feels like the opposite of Brownian motion. It holds its shape. Push on it gently and it resists. Leave it alone and, relative to the desk, it can remain perfectly at rest for hours. Yet its atoms are not frozen into classical immobility. In a solid, atoms occupy positions within an ordered structure. At ordinary temperatures, they undergo thermal displacement around their equilibrium configurations. The object can have zero bulk velocity relative to the table, while its internal degrees of freedom remain active. This is not a philosophical inference from the idea of motion. It can be measured. In the early 20th century, Peter Debye developed the mathematics describing how thermal motion affects the diffraction of X-rays by crystals. What became known as the debye-waller effect links atomic displacement to changes in diffraction intensity. Later X-ray and neutron measurements made those atomic displacements quantitatively accessible. That gives us a second, independent route to the same broad insight. The liquid looked still, yet molecular agitation revealed itself through Brownian motion. The solid looked still, yet atomic displacement reveals itself through diffraction. Different mechanism, different experiment, same warning about scale. But there is a subtle mistake hiding here too. It is tempting to say, then the solid is not really at rest. That is not correct. Rest is a relation. The metal bar can be at rest relative to the desk. Its center of mass can remain stationary in that frame. At the same time, its atoms can have internal thermal motion. Both statements can be true because they describe different levels of the system. This distinction becomes even sharper in special relativity. Einstein's other famous 1905 paper rejected the idea that physics needs one privileged state of absolute inertial rest. But relativity does not say that nothing can ever be at rest. A cup can be at rest relative to a table. The table can be moving relative to Earth's center. Earth can be moving relative to the sun. There is no contradiction because at rest is incomplete until you specify the reference frame. That means the defensible principle is not nothing is ever still. It is more precise. Stillness depends on scale and reference frame. Something can be stationary as a whole while remaining dynamically active within. If that sounds abstract, remember where this video started and what the scanner was reading while you held still. Return to that scanner for a moment, because it is a test of language as much as a test of tissue. Diffusion MRI is designed to detect the random displacement of water molecules through tissue. Magnetic field gradients make the MRI signal sensitive to molecular motion, allowing researchers and clinicians to infer features of tissue microstructure. The method does not require the body to sway, pulse visibly, or vibrate as a whole. The person can lie still, while molecular diffusion remains measurable throughout living tissue. So if someone says, "Your body is moving even when you are still," that can be physically true in one specific sense. Molecules inside the body continue to diffuse and participate in thermal motion. If that sentence is immediately turned into, "Therefore your thoughts emit a frequency that attracts matching events," the evidence has been left behind. The first statement identifies a measurable process. The second introduces a new causal claim. Those are not the same thing. Physics is full of transitions like this, where a word begins with a precise meaning and then quietly expands. Energy becomes mood. Frequency becomes attitude. Resonance becomes agreement. Quantum becomes possibility. Metaphors can be useful. They can even be profound. But a metaphor does not inherit the experimental status of the mechanism it borrows from. To see why, consider one of the most visually persuasive experiments ever associated with vibration. The Chladni plate. It makes invisible mechanical motion visible. It is real physics, and it also shows exactly why visual similarity can mislead. In 1787, Ernst Chladni published foundational experiments on vibrating plates. A plate is driven mechanically at a suitable frequency. Sand scattered across its surface begins to move. As a standing wave mode forms, some regions move strongly while others move very little. The sand is shaken away from the strongly moving antinodes and accumulates along the nodal lines. The resulting geometric figures can look almost impossibly ordered. Change the driving frequency and the pattern changes. Change the plate geometry or boundary conditions, and the allowed modes change. The system has preferred patterns of motion, and resonance can amplify them. All of that is established mechanical physics. But notice what the demonstration does not show. The vibration does not create the plate. It does not create the sand. It redistributes existing material under a driven mechanical process. It also does not show that all frequencies attract their like. Resonance is not a cosmic rule of similarity. In mechanics, resonance occurs when a system is driven near one of its natural frequencies, and the coupling conditions allow energy transfer. The word has constraints. There is another irony inside the experiment. Chladni figures are famous as proof of vibration, yet the sand collects along nodes precisely because those regions have very small displacement for that mode. The pattern depends on a contrast between regions of stronger motion and regions of relative stillness. So even here, everything is vibrating equally is the wrong picture. Real systems have structure. They have modes, boundaries, amplitudes, nodes, damping, coupling, and specific measurable variables. That complexity is not a nuisance. It is what makes the physics explanatory. And it prepares us for the most difficult case of all. What happens when thermal motion is pushed toward its minimum? If hidden motion were only a consequence of heat, then a simple thought suggests itself. Cool the system enough, and perhaps motion should disappear. Classical intuition points that way. Lower the temperature, reduce thermal agitation, approach absolute zero. Quantum mechanics changes the answer. For a bound harmonic oscillator, the lowest possible energy is not zero in the classical sense. The ground state energy is 1/2 h bar omega. The system retains non-zero quantum uncertainty even after ordinary thermal excitation has been suppressed. This is often described as zero-point motion, but the phrase can create a misleading cartoon. A quantum ground state is not necessarily a tiny object visibly shaking back and forth along a classical path. A stationary quantum state can have a time-independent probability distribution. What remains are irreducible quantum fluctuations and non-zero uncertainty in the relevant observables. That distinction is essential because this is where metaphysical claims often attach themselves to quantum language. In 2010, Andrew O'Connell and colleagues reported bringing a mechanical resonator into its quantum ground state and controlling single quanta of vibration. Later, optomechanical experiments resolved ground state or vacuum fluctuations in mechanical systems with extraordinary sensitivity. These are genuine quantum effects. They do not show that thought can manipulate a universal zero-point field to reorganize external circumstances. They do not establish a hierarchy in which emotions occupy physically higher or lower frequencies. They do not prove that consciousness is mechanically resonant with wealth, relationships, or future events. The experimental result is both narrower and more interesting. In appropriate bound quantum systems, removing thermal excitation does not reduce the system to a classical picture of perfectly definite position and momentum. The deeper lesson is becoming clearer. At each scale, reality may remain dynamically structured beneath an appearance of stillness. But the mechanisms are not one thing. Brownian diffusion is stochastic transport. Atomic thermal displacement in a crystal is lattice dynamics. Chladni patterns are coherent standing wave modes. Relativity is about the structure of space-time and reference frames. Quantum ground state fluctuations arise from quantum mechanics. Calling all five vibration does not unify them. It erases the differences that make each one scientifically meaningful. So where did the idea of a single universal vibration law come from? The phrase most people now recognize comes from the Kybalion, published in 1908 under the name Three Initiates. Its principle of vibration declares that nothing rests. Everything moves, everything vibrates. The book then extends the idea across matter, energy, mind, and spirit. It presents differences between levels of reality as differences in rate of vibration, and suggests that mastery of mental vibration can alter mental states and even affect broader phenomena. As history, that matters. It tells us what the authors taught. It does not tell us that physics experimentally verified the teaching. The timing is revealing. The book appeared in an era when electrons, atoms, radiation, the ether, and new theories of matter were transforming the public imagination. It borrowed scientific language available at the time, including concepts that modern physics later revised or discarded. Older Hermetic writings genuinely contain ideas about cosmic motion, generation, and change. So it would be wrong to pretend that philosophical reflection on a moving cosmos began in the 20th century. But it is equally wrong to project Brownian motion, relativity, quantum mechanics, and modern resonance theory backward into one ancient scientific doctrine. The historical chain is not a single line of experimental confirmation. It is a sequence of different traditions using some of the same words. That is why the phrase law of vibration can sound scientific without having one agreed scientific definition. A physical law needs operational content. It tells you what quantities exist, how they relate, under what conditions, and what observation could prove the prediction wrong. A universal emotional or spiritual frequency law would need the same treatment. What variable represents an emotion? What instrument reads its frequency? In what unit? What field carries the interaction? How does it couple to distant external events? What result would count as failure? Until those questions have answers, the claim remains interpretation, not established physics. This does not make the interpretation meaningless. It simply places it in the correct category, and once that category line is clear, something more useful appears in the evidence. Take the strongest examples together, but do not force them into one mechanism. A suspended microscopic particle wanders because of molecular collisions. Atoms in a rigid crystal show measurable displacement distributions. Water molecules diffuse through the tissue of a person lying still. A driven metal plate organizes itself into standing wave modes. A quantum mechanical resonator retains ground state fluctuations after thermal excitation is strongly suppressed. And special relativity gives no privileged inertial frame that deserves the title of absolute rest. These phenomena are independent. They were developed in different theories, measured with different instruments, and described with different mathematics. Yet they converge on one conceptual correction. Human perception is optimized for a narrow scale. We detect the table as solid because, at our scale, it is. We detect the glass as still because, at our scale, it is. We experience our body as motionless because, at our scale, it can be. The error begins only when a scale-specific description is mistaken for the complete physical description. That is the durable lesson. Stillness is not an illusion. It is a level of description. Motion underneath it is not a contradiction. It is another level of description. The same object can support both. This is more powerful than saying everything vibrates because it gives you a rule for thinking instead of a slogan. When a claim crosses scales, ask whether the mechanism crosses with it. If molecular motion exists inside matter, that does not automatically create a physical frequency for an idea. If mechanical resonance organizes sand, that does not automatically create resonance between a belief and a future event. If quantum fluctuations survive in a ground state, that does not automatically create a channel through which intention controls reality. Each bridge has to be demonstrated. Without the bridge, the similarity is conceptual, not causal. That single discipline prevents two opposite mistakes. One mistake is to dismiss invisible dynamics because ordinary senses cannot detect them. The other is to use real invisible dynamics as permission to believe any invisible mechanism at all. Science became powerful by refusing both. It trusts what measurement reveals beyond perception, and it demands evidence for every new causal step. That leaves one final question. What should actually change once you grasp this? The practical change is not to walk around believing that everything secretly has one mystical frequency. It is to stop confusing appearance with mechanism. The next time something looks completely still, choose one example and describe it at 3 levels. Take a glass of water. At the human scale, it may be stationary relative to the table. At the microscopic scale, molecules are thermally active, and suspended particles would undergo Brownian motion. At the theoretical level, that microscopic agitation has measurable statistical consequences that can be calculated and tested. Now do the same with a metal object. At the human scale, it is rigid and still. At the atomic scale, its atoms have measurable displacement distributions at ordinary temperature. At the experimental level, diffraction can reveal those displacements. Then apply the same discipline to any larger claim that borrows scientific language. If someone says a thought has a frequency, Ask what oscillates. If someone says two life events resonate, ask what coupling transfers energy or information. If someone invokes quantum fluctuations, ask what specific experiment connects those fluctuations to the claimed effect. Do not reject the claim because it sounds strange. Do not accept it because it borrows a true word. Ask for the bridge. That is the part of the 1905 story worth keeping. Einstein took an invisible mechanism and forced it to produce a number. Perrin took that number into the laboratory and tested it against reality. The result was not a slogan about universal vibration. It was a method for seeing beyond appearances without abandoning proof. Once you start using that method, the world around you does change. Not because your thoughts physically tune the universe, but because still, solid, empty, and obvious stop being final answers. They become questions about scale, frame, mechanism, and measurement. And those questions are where the hidden structure begins.